Good morning. Hope everybody's doing well this morning. We have another wonderful week of Chem 100 ahead of us, and we're going to start today with looking at some ionic and covalent compounds and how to recognize them, how to name them, and how to put them together and write formulas. We'll wait a minute or so and see if some more people join in, and then we'll get started. If you're following along, this should be handout 4. As usual, I am monitoring the chat if you want to leave anything in there, as well as I'll hear messages pop up in Discord if you'd rather leave them there. Please let me know, as usual, technical difficulties, if you can't hear me, if you can't see me, things like that. All right. Looks like somebody is here, so we'll get started. And hopefully some more people will join in as we go. As usual, this will be recorded, so those of you who can't make it are watching it later. So hello to you as well, whenever you happen to be watching us. All right, so just as a quick review from the last stuff. Hey, good morning. Morning, Daisy. Good morning, Maria. As a quick review from the last stuff, we talked last time a little bit about the organization of the periodic table and some of the different ways that we name these compounds and how they behave. And the key difference for us today with the stuff that we're going to be doing in this unit is differentiating metals and nonmetals. So if you recall from before, the metals are all over on this side, and the nonmetals are over here. These ones in the middle here we called metalloids or semimetals, kind of the in-betweeners. And then one interesting exception that you'll see if you look at it, like when you looked up those categories in the periodic tables, is hydrogen. Hydrogen is over here because when you look at its electrons, it kind of makes sense to be in that category with the one valence electrons. Everything in that group has one valence electron, but it really is a nonmetal. Hydrogen's not a metal. So even though it's over here, it's really in the nonmetals category. Everything else mostly fits as we would expect. All right, so now we're going to do a little activity distinguishing ionic and covalent compounds. So first we're going to look at some covalent compounds. Here's 3 examples of what we call covalent compounds. And I know we haven't defined what that means, what a covalent bond is. We'll get into that in a couple of chapters. But to identify these compounds, we want to see what these have in common. So let's look at the elements in this molecule. So methane, we've got carbon and hydrogen, and those are nonmetals. Sulfur difluoride over here, we've got sulfur and fluorine, which you can see from the formula here. If we look back at the periodic table, those are also nonmetals. So if we take that information together, what generalization can be made about the elements in covalent compounds? In general, we can say those are nonmetals. Now, that's going to work fine for this class. It's a bit of an oversimplification. Other metals can covalently bond as well. But for the compounds that we're most concerned about in this class and the things that we're going to be looking at, we're going to focus on the bonding of nonmetals, and so the covalent bonding of nonmetals. So when we see compounds made entirely of nonmetals, we're going to call those covalent compounds, right? And that describes the interaction of the elements. Again, we're not going to define exactly what that is just now, but it just is a way to categorize them. So if you have a compound made entirely of nonmetals, we can categorize them for now as a covalent compound, which will affect how we're going to name them. All right, so look at the difference between that and these structures of ionic compounds. So one thing you can see right away is the discrete separate molecules here. Not all covalent compounds are discrete separate molecules, but ionic compounds are always these more ordered cage-like structures, at least the crystalline ones are. So you can see instead of like individual little bits that are connected together, we have ions, barium and oxygen in this case, kind of interspersed between each other in a large structure. Same thing with potassium and fluorine and sodium and chloride. Depending on how small we make our balls, we have a little bit different structure here. But the lines that are shown here are not indicating bonds, like covalent bonds, like sharing electrons. Those are just kind of to show you what the overall structure looks like, to show you that it's cubic. So as opposed to the other ones before, we see here that these are now made of a metal and a nonmetal. So look at each of these structures: metal, nonmetal, metal, nonmetal. And we're going to see, again, a couple exceptions to that, but generally, we can generalize that ionic compounds are a metal and a nonmetal, but be careful with this one because we will see where that kind of doesn't quite make sense. But what we can say for sure is that ionic compounds are made of ions, charged particles, positively charged cations, negatively charged anions, packed together in a structure. All right, so we talked about cations and anions a little bit last time. And if we look at these 5 written ionic compounds, you'll notice that the cation, the positively charged ion, is always written first. Oops, it said circle, but I underlined them. You can circle them in your copy. So that cation is always listed first. You'll also notice that the cation is often described as the metal. And it's true that there are cations that are not metals, but when a metal is an ion, for our purposes, it's always going to be a cation. It's actually quite rare to have compounds with metals that are not, that are anions, that are negatively charged. So if we look back at our periodic table here, when you see any of these metals in a compound like this, they're generally going to be listed first, and they're going to be the cation. So that's how you can determine which is the cation, which is the anion. And you can use your own opinions for those kinds of things. So let's look at a quick checklist here. And I'm going to put a check where things are definitely true, and then something else where they're not true. So ionic compounds can contain metals. Covalent compounds, I'm going to put like a dotted check because metals can be in covalent compounds, so I'm not comfortable just saying that that's wrong. But for our purposes in our class, we're not going to see those kinds of compounds. So we can say if we see a metal, it's going to be an ionic compound. Nonmetals are going to be in both types of compounds. Generally as the anions in ionic compounds, generally, with one exception, and as everything in the covalent compounds. Contains only nonmetals, that's generally going to point to covalent, but it's also going to sometimes be the case for ionic compounds because there are covalent ions. Ionic compounds contain cations and anions, and covalent compounds do not. So when we talk about covalent compounds, we are not going to see cations and anions. And individual molecules are something that we will see in covalent compounds, but something we will not see in ionic compounds. All right. So using those rules, sorry, I just got a message, so I had to check it. Using those rules, we can look at these compounds and decide which ones are ionic or covalent. So before I do that, I want you to give that a try. If you're watching along, go ahead and try that. If you're watching this later, just pause the video or something and see if you can figure those out. And then I'll go through them and we'll see if we agree. All right, you have a chance to look through those. Let's see. So KBr, I'm going to say that looks like a metal and a non-metal. So I'm going to guess that's ionic. CO, that's two non-metals. Call that covalent. Aluminum and oxygen, I'm going to call that ionic, although realistically that's a little trickier, but we're going to refer to that as ionic. NH3, all nonmetals, covalent. CaCO3. Now this one's got some metals and nonmetals and 3 different elements. We're going to talk about those types of compounds in a little bit. But for now, we can still say that with good certainty that that's an ionic compound because of the calcium here. So ionic. And then Ni3, that's going to be 3 nonmetals, covalent. And again, to determine, if you're having trouble determining what's metals and what's nonmetals, we can look at the periodic table for that and just use those 2 sides of that line. All right, I'll let you figure these out in these pictures. I think you can compare them above, and that'll make sense. So before we go on and talk more about ions and naming, is there any questions about that classification? Are there any questions about that classification? Yeah, if it has both metal and nonmetal, we're going to call that ionic. Anything else? All right, let's move on. You can always jump in if you think of something you want to ask. So we saw a table kind of like this in the last handout, with more of the specific elements listed in there. It's actually came from the textbook. I just want to let's refresh our memory on this. Remember that these elements here are going to generally take a +1 charge, +2, +3 is a little bit trickier because it really it's only for aluminum, because that's really the only metal here. Or I'm sorry, that's not the only metal here, but that's the only one that with a reliably +3 charge always. The +4s, I'm going to kind of cross that out. +4, -4 is kind of a tricky element. It's kind of a tricky charge because it's such a high charge. And those elements don't really quite, the ones lower in the group get a +4 charge sometimes, but it's not something that's going to concern us. And then we can look at +3s down here, +2s down here, and +1s. Or, I'm sorry, -3s, -2s, and -1s on those, just like in the previous one. And if you want to know some more specifics about that, look at that table in the previous handout. But this is just kind of to refresh our memory. Okay, let's get on to the naming part. Now this looks like a lot, and this is always kind of a tough part of the course, but we're going to take it step by step and we'll be okay. So what you see behind me here, this is from some textbook, and it kind of summarizes everything about all the different ways you can name things, and it kind of works like a flow chart, so you decide which category it's in. And as you can see, it looks like a lot, and it may or may not be helpful for you to see it in this form. So we're going to go through it bit by bit, And if you want to come back to this as an overall summary, you can. If you find that just overwhelming and confusing, then don't worry about it. But it's not like you need to memorize this whole chart. We'll talk about what you need to do. Okay, so first of all, the first step when we're looking at naming compounds is to decide if it's ionic or covalent. We just talked about that. So again, for ionic ones, we're going to look at a metal and a nonmetal, or more specifically and correctly, two ions. And if it's covalent, that means it's going to generally be all nonmetals. Okay. So I actually, this table kind of comes from someone else. I don't find it super helpful. We're going to kind of come back to it in a little bit. So I'm going to skip over this for now. Actually going to skip over all this stuff for now. Before we get into the names, I want to look at how we put chemical ionic formulas together. So take a look at this table here. If we have a cation of Na+, and actually I'm going to zoom in on this a little bit so that we can, because we're actually not going to worry about the name just now. We're going to say if we have an Na+, a sodium cation, and a Cl- anion. A couple of things we need to know about that. One, that the cation always just keeps its name. So sodium, the neutral atom, is the same, is called sodium, and sodium plus the ion, the cation, is also called sodium. But anions change their name. So if you look at the periodic table, this is known as chlorine, but the Cl- anion is known as chloride. So we cut off the end and put "ide" on it. Same thing here. We've got iodine becomes iodide. Phosphorus becomes phosphide. Nitrogen becomes nitride. So we take the ending off the element name and put "ide" when it is an anion. And then when we think about how to combine these into a chemical formula, we have to keep in mind that the chemical formula has to have an overall neutral charge. We'll see some exceptions to that later, but for now, the chemical formula always needs a neutral charge. So, for instance, if we have +1 sodium and -1 chlorine, then we need one of each to make an overall zero charge. So we've got +1, we've got -1, and so the overall charge of that compound is 0. If we have barium, which is a +2 ion, it's in the alkaline earth metals in column 2A. If we have barium combining with iodide, now we have a +2 barium and a -1 iodine. So in order to make that equal 0, overall neutral charge, we have to actually multiply that by 2. So that's where this 2 comes from. So when we put together these formulas, we need to make sure that the overall formula is balanced. And there's one nice little shortcut for that, which mostly works as long as you remember one thing, and that is number 3 here. When writing the chemical formula of an ionic compound, you crisscross the charges and remove the pluses. So the example given here is aluminum oxide. Aluminum is 3+, oxygen is 2-. In order to balance those charges, really what we're doing is we're trying to find the least common multiple. That's kind of the math term for it. But what we can do just functionally to make that happen is we can take the 3 from the aluminum and make it the subscript of the oxygen. We can take the 2 from the oxygen and make it the subscript from the aluminum, and we end up with the formula Al2O3. Now let's look at why that works. So aluminum is +3, and we're saying there's 2 of them. Oxygen is -2, and we're saying that there's 3 of them. So there's 2 aluminums and 3 oxygens. So that's +6 overall and -6 overall. +6 and -6 is 0. So the overall compound is neutral. And that kind of answers this question too. Why do the charges go away? Well, the overall compound is neutral. So in the individual ions, we have charges, but when we put them together, we make a neutral compound. And that is why we have ionic compounds in the first place. Free ions can attract each other to form the ionic compound together. So this crisscross thing, let's check it down here too and make sure it works. And I don't have a lot of room to write over there, so I'm just going to do it over here. Let's check with like that barium one that we just looked at. So we've got barium 2 plus and iodide -1. So we're going to put the 2 down here and the 1 over there. If there's a 1, we generally don't write it. So that compound is going to be Ba1, which we're just going to leave alone, I2. All right, questions about that method? Does that make sense so far? Okay, thanks. All right, so it's not really an exception to the rule. It still works, but there's a few compounds where this gets a little bit, it doesn't quite work the way you might want it to. So for example, if we had an ion copper +2 and oxygen minus, whoops, -2 minus, and oxygen -2. If you're really set on this crisscross method, that would mean that you put the 2 here and the other 2 there. And that would give you Cu2O2. Now that's really not the correct formula for this compound, and the reason is because an ionic compound, the subscripts don't mean the individual numbers of atoms. It just means the ratio between the two atoms. So if the ratio is 2 to 2, that's really 1 to 1, right? So it really should be CuO. And if you're just looking at the charges and you're not too attached to the crisscross method, you should be able to see that if you have a 2 plus and a 2 minus, you can just put them together 1 to 1 and get a neutral compound. But if you're really like always going crisscross, 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 you could accidentally leave this as Cu2O2 when it should really be reduced to the lowest possible numbers. This can also come up with some like 4 plus and 2 minus, or so if you had 4 plus and 2 minus, you'd end up with subscripts of 2 and 4 when they should really be 1 and 2. So just watch that. If you have a neutral compound, just make sure that your numbers are reduced to the lowest possible ratio. Okay, so that said now, let's see if we can do the first couple columns. Actually, we should be able to do the whole thing here. Not the names, so skip the name blanks, but let's see if you can fill in the rest of this right here. So these 3 chemical formulas and these 2 cation and anion. All right, let's see how this went. So for the first one, we've got magnesium and phosphide. Magnesium 2 plus, phosphide 3 minus. So if we've got a 2 plus and a 3 minus, that means we need 3 of these and 2 of these. So we cross those and get Mg3P2. For potassium, we have +1, nitride -3. So we need 3 of the +1s to balance out the -3. So that's going to look like K3N. All right, hopefully good so far. Notice I didn't write the charges here because once we have the compound is neutral, and the charges aren't there anymore. All right, and then the last one, we're given the name aluminum fluoride, and then it's up to us to find the ions in the formula. So to do that, we're going to use our periodic table. So aluminum fluoride, I'm going to look up on my periodic table, and I can see aluminum right there and fluoride right there. So aluminum, that's column 3A, and I know that that's a 3 plus ion. Fluoride over here in 7A, that's going to be a -1 ion, just like all of those in that category. So I write those ions first. Aluminum, I figured out was 3 plus, and fluoride, I figured out was -1. So then putting those two together, I need 3 of the -1 to match the or balance the +3. So that looks like AlF3. Any questions about those? Putting those formulas together? All right. So now let's look at the last part, which is the naming. So the way that this document summarizes these is with this kind of a graphic. We have to actually, there are different naming rules for different types of compounds, which is why we spent so much time thinking about ionic versus covalent. Once we decide we have an ionic compound, then we use these particular naming rules where we say the name of the cation and then the base name of the anion plus ide. Right? So you've got calcium, you've got iodine, you cut off the ine and change it to ide, and so your name is calcium iodide. Simple enough. So let's fill this table in with those names. First, let's look at the ones that are already done for us. So we've got sodium chloride, magnesium phosphide, aluminum fluoride. And the ones that are missing here are going to be barium and iodine, which we call as a compound barium iodide. Potassium and nitrogen becomes potassium nitride. When you're working through these things, remember, use your periodic table. It's always going to be there to help you, so you might as well use it. You don't have to memorize these names. A lot of them you'll just know because we'll use them so much in class, but use your periodic table. You've got it. Use it. All right, and then you can go through and practice some of these as well. This is wrong. Why is this here? Oh, that's right, we skipped this part. Okay, so let's go back then and look at what happens when we have a covalent compound instead. So once we decide that we have a covalent compound, the naming works a little bit differently. And this is actually an important way to distinguish between these types of compounds. For a covalent compound, there isn't a set number or there isn't a set ratio. So like, for instance, with phosphorus and oxygen, there are various different compounds of phosphorus and oxygen that have different numbers of phosphorus and oxygen, and so we have to have a way to name those things. As opposed to, let's say, sodium and oxygen, there's only one possible way those can go together, so we can just call that sodium oxide. So when we talk about covalent compounds, because there's all different possibilities for these numbers, we don't mess with the charges at all. Instead, we just use a prefix on each element to tell us how many there are. And these prefixes come from what you might have learned in geometry in the past, like with these different shapes. So just to review, of course, triangle. Yes, this is a square, but so that it fits in this pattern, we're going to call it a tetrahedron. Pentagon, hexagon, heptagon, octagon, nonagon, decagon, etc. I don't know if you remember those names, but the important things are these last two columns. When we have a certain number, we can fill in these prefixes. And those prefixes are going to be penta, hexa, hepta, octa, nona, and deca. And so we're going to use those same prefixes to talk about the compounds. So if we see OCl2, we're going to call that we have one oxygen, monooxygen, and we have two chlorines, dichloride. Now, so we could maybe call this one monooxygen dichloride. Now, a couple things to keep in mind here. If the first element has only one atom, we've dropped mono. Otherwise, there would be way too many compounds that all start with mono. So we would just call this, there it goes, oxygen dichloride. P4O10 would be tetra phosphorus. Decaoxide. Actually, I think that one's left there. And then this one would be nitrogen trifluoride. We can also go the other way, and we can look at those names and then write the formulas. Sulfur dioxide, SO2. Dinitrogen tetroxide, 2 nitrogens and 4 oxygens. Selenium dioxide, 1 selenium and 2 oxygens. So once you know those prefixes, that method is pretty simple. The thing that throws people off most and a source of a lot of errors here is mixing up the two ways of naming. And specifically, everybody likes this one the best because it tells you exactly how many of each element there is. So everybody sees that and says, oh, okay, well, I should just call this barium diiodide because there's 2 of them. But that's not right because with ionic compounds, we don't use those prefixes. So let's make a little note to ourselves here. Those prefixes are only for covalent compounds. All right, only for covalent compounds. So that's why it's important to first categorize the compound as either ionic or covalent, and then deal with the naming, because which category that goes in is going to change the rules you use to do the naming. And only if it goes into that covalent category are you allowed to use these prefixes. All right. So those are the basic naming for those types of categories. One thing to note here, the ionic type of naming that we did right just now is when the ion only forms one type. So all those predictable ones that we looked at earlier up here, those are the ones, compounds with those cations are the ones that you can name using the rules we just talked about. All the ones in the middle here that can have multiple different ions, like they can be +1 or +2 or +3 or whatever, we need to change the rules a little bit because because we don't know. If you just say iron's one of these. If you say iron chloride, that's ambiguous because there are two different compounds of iron chloride depending on the charge of iron. So we're going to get into that next time. We'll do that Thursday evening. For now, focus on these two. It would be really great if you can work ahead a little bit and practice this. There's also, beyond the Mastering Chemistry, there's an additional practice sheet on Blackboard for doing the naming. And we'll look at that a little bit on Thursday, but if you can pull it out before that and just try some yourself, that'll be a good way of figuring out what your strengths and weaknesses are with regard to the naming, and hopefully you'll come with some good questions on Thursday. So are there any questions now before we say goodbye for today? All right. Oh, Daisy has a question about the handouts. Yep. It doesn't matter. What you can ask it now or you can send a message later. All right, let me pull that one up. H2. The temperature equations. The temperature equations, you should know how to do those, but you don't need to memorize the equations. So you'll have the equations, you just need to know how to use them. Not the temperature. Which, am I missing a page or something? I only have page 9, up to page 9 here. What, do you have something after this on your... Okay, yeah, show me what you're talking about, and we'll move it to Discord. All right, well, thanks everybody, and I will see you. I'll see half of you tomorrow, and anybody else who wants to join in Thursday evening at 7. Bye.